Thank you, Glenn. Please do ask questions. The more interactive, the better. So we'll just wait for the slides to come up. So whilst they do, Glenn is right. I'm a colorectal surgeon, and I spend most of my time operating on bowel cancer, which is a terrible disease. So like all good speakers, I'm not going to talk about what I've been asked to talk about. So this is the title, all right? I'm going to talk about something subtly different, all right? So I'm really going to talk about this, because I believe the greatest gift in the discovery of, well, the rediscovery, really, of the gut microbiome is not in the treatment of disease, it's in the prevention of disease. And I believe the gut microbiome to be a critical mediator of cancer risk, and really we need to start leveraging the gut microbiome to reduce the cancer burden. And that's really what I'm going to talk about. I'm not going to talk exclusively about colorectal cancer, because I'm going to make some other examples. So I was strolling along this morning, and I saw this outside the Wellcome Trust, and I thought, gosh, how wrong is that? So you are highly individualized, obviously, as you well know, and of course your DNA is important in determining exactly who you are, but actually there's infinitely greater variation in your gut microbiome. It's much, much more personalized. And the gut microbiome is the key to unlocking the potential of personalized healthcare and precision healthcare. And what I'm going to explain in the next 20 minutes or so is the challenge of trying to do that in cancer and why that's so important. All right, so let's cut to the chase. So you've heard very eloquently from the three speakers this morning about gut microbial complexity and the challenges around gut microbial evolution, particularly in early stages of life. Just one quick caveat to this talk. The gut microbiome does not just mean bacteria. I'm predominantly going to talk about bacteria. I don't have time to talk about the virome and a whole bunch of other interesting things, but please be aware of that. The second thing is there's a lot of complexity and confusion. As you've heard this morning, what's in the right side is different to what's in the left side, and as you will not be surprised to hear, the type of cancer you get in the right side is therefore different to what's in the left side. What's in the rectum is different to what's in the cecum. And we are trying to unpick some of this complexity. I'll explain a little bit more about what we're doing. If you go to an American meeting, they talk about dark matter. And that's because we still don't really know who's there, let alone really what they're doing in terms of gut complexity. And you have to put the work that we're about to look at in perspective, which is that we really only discovered the gut microbiome again properly in its detail around 10 or 12 years ago. So actually we're still at the infancy of the science. Caveat number two is that cancer is a complex treatment journey, okay? And most of the work that you will see is analysis done at this stage. So the diagnosis has happened, right? And that usually means by the time we're sampling the gut microbiome in these patients, the horse has already bolted quite firmly. And really, we don't understand quite often how long it takes to get from cancer initiation to actually clinical manifestation. And it's this bit that's the bit that's really important. So we're not really looking in the right place at the moment. And the other thing to say is that survivorship and function after surgery, after treatment for cancer, is really, I think, also importantly linked to the structure and function of the gut microbiome. So the gut microbiome has implications in the entire length of the patient journey, and we can unpick where we want. So this is a bit that I want to focus on. There's a lot of young people in the audience here that will qualify as millennials. And if you're a young person, you should be worried by this slide, because the rates of rectal cancer are climbing spectacularly in your age group. We have a growth of 4 times the risk of rectal cancer than someone born in the 60s or 70s, right? And it's the same for colonic, but rectal cancer is going up a bit faster. This is not a genetic phenomenon, okay? This is an environmental exposure phenomenon. This is a global issue. If you're in Africa, Africans typically died, unfortunately, from malnourishment, from malnutrition, from pathogens, from infectious diseases, but they now have a burden of Western diseases. And we predict an 85% increase in their cancer burden risk by 2030. So we've got global changes in the epidemiology of bowel cancer. We've got generational changes in the epidemiology of colon cancer. And why is that happening? We think the gut microbiome might be important. So this is work by my collaborator, Steve O'Keefe, and he went off and he sequenced a bunch of rural Africans from KwaZulu-Natal. And you notice my entry slide had a picture of Africa. And I think Africa is really important for understanding how we can protect ourselves against colon cancer risk. And you can see that Africans, compared to African Americans, have massive amounts of Prevotella versus Bacteroidetes. And this sort of maps loosely onto colon cancer risk. Now, one of the speakers this morning made the really critical, important point of highlighting the fact that really when we talk about phyla or phyla level changes, we're massively misrepresenting the complexity of what we're looking at. So this was a nice paper that came out in Genome Medicine a few years ago, and it looks at different kind of species expressed across different populations across the globe. And you can see that when you get down to a species level, there's still massive variation in the structure and function of the gut microbiome. In fact, it's even greater. In fact, it's mind-bogglingly complicated. So these are Chinese people who, when you look at Eubacterium rectale, and you've just heard an awful lot about that, the types of species that they have there are structurally and functionally different. And I'll explain why that's important as we go. So the global microbiome is important. So this is work by my colleague Julian Marchesi, and he sort of coined this idea of passengers and drivers, or drivers and passengers. So in trying to understand why people get cancer, he had this idea that maybe what happens is that through your lifestyle, maybe your genetic predisposition, a bunch of pathogenic toxin-producing bacteria predominate on the mucosa. They interact with the gut mucosa, and that triggers the formation of an adenoma, which is a precursor lesion of colon cancer. Cancer forms, and then the ecology of the mucosa changes again, because the relationship between the bacteria and cancer is important. It has a metabolic relationship. But those initial drivers possibly have gone. The ecology, there's been some sort of competitive inhibition of those bugs, and they disappear. So a lot of the work in this field has been trying to unpick driver-passenger relationships, because if you can find a driver for colon cancer, you can win a Nobel Prize for medicine, and you can be famous and rich and drive Ferraris. So there's lots and lots of these bugs that have been highlighted, okay, that seem to have specific pathogenic mechanisms that seem to cause cancer in mouse models, in cell line models, and not in, well, we'll get onto human models in a second, all right? But we know that they have these sort of core functions which seem to be important. The problem is, as has already been explained to you this morning, this really underestimates the complexity of the ecology of the gut. So this is these are my patients. This is of 154 patients with colon cancer, and we've sequenced the mucosal microbiome. And you can see phyla-level distributions across that cohort at the time of surgery. The problem is we have no idea what the consequences of this continuum really, really means. And often in the literature you will hear this word dysbiosis, which basically means an ecological imbalance associated with a pathogenic state. I believe dysbiosis to be an inaccurate term, and we've kind of abandoned it really, because you're saying, well, yeah, you've got a bit of ecological diversity that's not quite normal, whatever normal is. Still no one can tell me what a normal microbiome is. It doesn't really tell us anything at all about mechanism. There's a massive gap between the two slides that I've just shown you, and I think we should abandon the term. So this is data published by, well, not data, this is an image published from Joel Duray, and it was on the application of fecal microbiome transplantation in patients with hematological cancers having bone marrow transplants. And there's a typical sort of balance between the protective and the aggressive immune response that you need in these patients having this treatment. And what's interesting is that you can predict survival basically based on ecological diversity within the gut, right? And patients before transplant have large amounts of enterococci, basically do very badly, and they die. And those that have, different distribution of lactobacilli and Clostridium seem to do a bit better. And he was arguing, well, if you get down here somewhere, maybe you can give an FMT and that improves survival. And lo and behold, it does. Actually, you can do that, and it does improve survival. Again, the problem is that that really enough for a clinical study? Is a measure of ecological diversity going to get us through an FDA approval process? Does it really tell us about mechanism? And I'm not convinced it does. So let's just flip back to bowel cancer for a little bit. This is work done by Paul O'Toole's group, and I'm sure you guys will be familiar with Paul. He's done a lot of work in this field. So he kind of did one of the early studies. He said, look, okay, let's look at mucosa, let's look at feces, let's look at left, let's look at right. Is there any sort of commonality? And you know, there isn't. What's in your proximal bowel is different to what's in your distal colorectal cancer. That's kind of obvious, right? There is a little bit of reflection between what's in your fecal microbiome and your mucosal microbiome, but not a lot. And you can differentiate, basically, colorectal cancer on the level of structures of the mucosa-associated bacteria co-abundance groups that you have. So effectively, you can kind of stage cancer. And we've repeated the same work. So this is work done by James Alexander, who just got his PhD. We're very proud of him. And he did a piece of work where he took about 180 patients. He looked at a UK cohort and also a Czech cohort. So these are patients with lymph node metastasis. So this is cancer has already spread out of the bowel. And you can see that when you look at, he's looked at two specific clusters, and I'll explain this data in a little bit more, but actually there seems to be a slight difference in the ecology between those patients who've metastasized and those that haven't. And when you look at other specific histological biomarkers of poor prognosis in cancer, we find that we get these sort of usual candidates, which I've described to you already, particularly Fusobacterium nucleatum, which is the sort of poster child of cancer work, particularly in the gut at the moment, that sort of has an association with stage. The problem is that this relationship is really quite complicated. It doesn't help us unpick the driver-passenger conundrum, because these cancers have already formed. And it also massively underestimates the importance of individual variation. So these Fusobacterium patients were only really found in about 20% of the cohort that we had, right? So we think that there's more to it than Fusobacterium, and we're not entirely sure as to why we see this relationship. So there's been a number of attempts to try and look at the molecular biology of cancer. So does the biology of the tumour define the microbiome that's on it? Or maybe we're just being a bit over-optimistic. Maybe this is all cancer-driven. So we talk about mismatch repair in colorectal cancer because that's kind of important. And we talk about mismatch repair deficiency or proficiency. And if you've got a mismatch deficiency cancer, there is a different distribution of bugs on it from those that are proficient. And what's important is that it's this chap again, Bacteroides fragilis. We see this time and time again in cancer. It's suppressed in those patients who are proficient, and increase in deficient patients. And it seems to be that there's some sort of metabolic relationship between these two states. So it's the production of amino acid peroxides for hydrogen sulfide that explain this link. So what it means is that the molecular biology of the cancer seems to influence mucosal ecology at least. Now, a major problem with studying cancer is heterogeneity. It's not only that no two cancers are the same, it's that within a cancer there's massive variation. So it's difficult to make kind of broad assumptions about a bug, cancer mechanisms. Now, there's been sort of big data attempts to try and define different phenotypes of cancer, and we have this term sort of CMS phenotyping, which is consensus molecular subtypes. That's what it stands for. And we've got kind of different subtypes, and we know that CMS4 have really a terrible relapse survival, and CMS1 also don't do so well. This particular is an amine phenotype. And so this was a group in New Zealand. They said, well, okay, let's look across phenotypes and let's see what sort of bugs predispose on these cancers. And lo and behold, if you've got CMS1, which has a bad prognosis, you have all the same sorts of nasty bugs that we demonstrated in our poor histological subtypes in our study. So we think that maybe it's the cancer biology that determines the sort of bugs that you have on the mucosa. What about when cancer's metastasized? I showed you that we'd identified subtypes for metastasis. So this was a study that came out in Science last year. It caused quite a palaver. It's good to know that you can publish in Science with n equals 10. So they prospectively took 10 patients and they looked at their primary cancers and their liver metastases. And then lo and behold, they both had Fusobacterium nucleatum with them. We don't really know what the significance of that is, right? So is this mechanistic? Are these just passengers zipping along through the metastatic route? But what's quite interesting is if you then pop that into an animal model and you pre-treat these animals with metronidazole beforehand, their cancer burden and their tumour volume goes down. It's an interesting idea that you might be able to prevent cancer metastasis through the use of antibiotics. Whether or not that translates into human studies is a wholly different picture. Okay, James, enough of this nonsense. Tell me about cancer causation. Well, here you go. Cancers don't just form, as I've described. You get an adenoma, typically, that progresses into cancer. And we know that these adenomas follow different molecular pathways. Okay, so there's a conventional pathway, what's known as a serrated pathway, which we know is a different phenotype, and actually we're changing our endoscopic screening pathway criteria on that basis. And then there's this sort of Lynch criteria, right? And Lynch criteria are germline mutations. So these are highly inherited cancers. We're not going to talk about them particularly. Just what's interesting to note is that this is what it looks like endoscopically. And this is a sessile serrated adenoma, and it's got a mucus cap on it. So it creates a completely different luminal environment for these bugs to biofilm-producing bugs to exist within, we think. So there have been some studies to try and look at adenomas. What's interesting about these is that these are controls. This is conventional adenomas, all right, and these are hyperplastic or sessile serrated adenomas. Is that we see differences between controls and patients with conventional adenomas, but we don't really see differences between the hyperplastic and sessile serrated, either in microbiome richness or, in fact, in diversity. So it's probably not what's happening actually on the mucosa of these adenomas that's critical. It might be that in the causation of cancer, it's actually something within the lumen of the microbiome that's driving that. So this is again work by James Alexander, and I mentioned that he'd done some, he'd sort of identified these clusters. So he'd identified these two clusters. One is what he's termed a benign cluster, and the second is a pathobiont cluster. And the pathobiont have quite a lot of oral bugs. So these are a lot of bugs that you typically find in the mouth. And in fact, when you look at other types of GI cancers, quite often they're found overexpressed within them. So upper GI cancers, pancreatic cancers, all right? So what's interesting is this in this graph here. So this is normal, low-grade and high-grade dysplasia, stage 1, 2, 3, and 4. And you just see almost a kind of linear drop-off of these commensal-type bugs. And you see a linear climb in these pathobiont clusters. And when you do a multivariate regression analysis, stage is the only thing that highly correlates with them. Obesity, smoking, ethnicity, all of these things don't seem to be important. So we think that a lot of the bugs that we're seeing in the literature are in fact passenger organisms. They're not driver organisms. And if you want to understand what's causing cancer, you've got to come back to this state. And that's the most important thing. Oh, one quick point. So we sequence all these cancers. And when you sequence these cancers and you look for kind of important genes that are critical in kind of cancer initiation and progression, there's no linear relationship. It's a mishmash of bugs. Some bugs are associated, some are not, some go up, some go down. And it's very difficult to unpick it effectively. We're trying to do that at the moment. So it's kind of complicated. So we got together and we said, okay, well, let's have a consensus statement. So CI UK kindly funded us to host a meeting in London in 2017, and we brought the world's experts to London, and we sat them around a table for 2 days, and we said, okay, is there enough evidence to suggest that the gut microbiome causes cancer? And the answer was not yet. And the reason is not that we don't think it does, because we do think it does. It's just that most of the studies have been done in animal models. They've been done in the wrong cohorts. They haven't been done longitudinally. And we don't have enough human data to unpick some of this complexity that we're currently seeing. And this gives you an idea. It is a map of complexity. Don't worry. You don't have to understand it. I barely do. So adenoma, cancer. This is patients where we've done LCMS metabolic phenotyping. So we've looked at metabolites, and then we've looked at the taxonomy of those cancers, and we've done a kind of network analysis. The only take-home message from this is that on cancer, the complexity of that relationship is really, really significant. In adenomas, it's not. So it means that as you go from adenoma to cancer, the host microbiome interactions are kind of important. Now, that might be critical for therapy, but it may not be so important for prevention. So prevention, we think we need to understand at a different conceptual level, right? There are lots of things that we know. I can reduce the incidence of colorectal cancer now without any knowledge of the gut microbiome. Just eat less crap, exercise more, don't smoke. You'll get less bowel cancer, right? And we know that all of these things are important. Now, there are some things that we know that are not important, like some of the xenometabolites that are within the environment. But really, the gut is a sort of chemical superhighway. It's an engine room producing bad secondary metabolites, some good secondary metabolites, and all of these things are constantly interacting with your immune system, as you've heard very eloquently this morning, right? So there is a network effect. There is a constant balance, and really cancer is an inflammatory disorder. It's the very end spectrum of inflammation, right? But in our group, we're trying to unpick these dietary, environmental interactions and trying to understand how the microbiome mediates them as you go from polyp to cancer. And constantly we're understanding new insights into the various mechanisms through which this works. Which takes me to Africa. Okay, I promised you we'd get to Africa. So we therefore study quite a lot of patients in Africa. So these are people preparing food in Africa. They do actually have quite a lot of commercial or synthetic prepared starches which they prepare. It's called their mini meal, and they turn it into putu. And we think that the preparation of these foods secretes quite a lot of the resistant starches into their diet. And so we studied these Africans, and we locked them in a house. And we compared them to some African Americans who we also locked in a house from Pittsburgh, and we put them on their home environment diet, and then we crossed over their diets, right? So we put them onto a very high fiber diet. So these African Americans have massive amounts of fiber, 55 grams a day, much, much higher than we typically consume in the West. So we would typically have, the average person will have 15 to 20 grams if they're lucky. The RDA is 30 grams, massive amounts. And low fat, low protein. And The poor Americans just couldn't cope with it. They bloated up, they were very miserable. The poor Africans were equally miserable because they just couldn't handle that much meat and fat. And as you can see, that if you go to America, if you hang out in London, the diet is pretty poor. So the significance of this is that diet is a really critical mediator of microbial secondary metabolism. So the implications for this for the mucosa are really significant. So this is Ki67, CD3, and CD68 expression between African Americans pre and post switch and Africans pre and post switch. And you can see that inflammation just goes up significantly in these Africans, and that it's completely reversible. And this was within simply 2 weeks of changing their diet. So if you make the diet change significant enough, you can influence inflammation and secondary biomarkers of colon cancer risk. And the reason is not because you're having massive changes in the structure of the microbiome. It doesn't actually change that much. We didn't see big changes in bugs going up or bugs going down. But what we did see is a change in the engine room of the microbiome. You change from a proteolytic to a saccharolytic engine room if you're an African American, and vice versa. And the metabolic consequences were dramatic. So bile acid secretion went up by 400% in Africans. Right? That can't be good. Equally, their short-chain fatty acid butyrate metabolism just dropped off a cliff. And these things were completely changeable. And you can see these are the metabolic phenotypes. So this is work done by Gia Lee and our PhD student in our group. So in rural Africans, you see these very significant changes in these secondary bile acids after this kind of quite large-scale dietary intervention. Choline was one of the only things that we really saw got dramatically in the urine of these Africans. And there's been a lot of interest in choline because of this story, so the TMAO story. So choline or carnitine is co-metabolized in the gut by bugs, which leads to TMA, which goes to the liver, which produces TMAO, which has been associated with heart disease, cardiovascular disease, platelet dysfunction, and also now cancer. Okay, so these are bug-driven metabolites which seem to be influencing cancer risk. And again, when you go to the big epidemiological studies, we see these hypotheses supported. This is the problem that we face in the world now. Okay, it's urbanization. It's urbanization on a massive scale. And trying to unpick diet from urbanization is quite difficult. Most of this is going to happen in the developed world. And really what's happening is an internal Armageddon, right? It's an ecological Armageddon. We worry about the environment externally, and the same thing is happening internally. And this is a good book. If you haven't read it, I highly recommend it. It's been going around for a bit. This is Marty Blasser's book on the disappearing gut microbiome. If you look at epidemiological studies, this is the nurses' study going back, I think, to the 70s, and they looked at around 16,000 women, and they looked at antibiotic usage. If you have antibiotics for over 2 months between the ages of 20 and 39, your risk of bowel cancer goes up significantly. So it's not just nutrition that perturbs the gut microbiome, it is an environmental thing, it is a toxin thing, it's a drug thing, it's a pollutant thing. And so we're now studying these patients as they migrate through rural into urban environments. So this is native Alaskans looking at rural Africans. Native Alaskans have a high-protein diet. They eat a lot of fish, they eat a lot of fat, they don't eat any fiber. And again, you will see changes in their diversity. And we're studying as they migrate from the northernmost town to which is really very, very cold. It looks like this in the winter, it looks like this in the summer, as they go into towns and cities. And as you go into a town or a city, your metabolic phenotype transforms. Part of the reason we weren't able to publish this because the native Alaskan group said, look, you're measuring drug metabolites, toxins like cigarettes and stuff like that in the urine, and we don't want to give our people a bad press. But of course, that's what happens. You go into an urban environment, you start drinking, taking drugs, smoking, eating bad food, and that turns up in your metabolic phenotype. So really, we can think about, just to go on from the speakers this morning, is that I think about the gut microbiome in a kind of quantum state. It's not constant. It's not on. It's not off. It migrates. As you heard this morning, what happens in your early phase of life is critical, and then you've got a lifetime exposure that at some point leads to cancer. The problem is that this is happening at the moment, and we don't know why, and we don't understand what the key drivers of this are. So the really important thing is how do we intervene to drive these people back up to prevent cancer, because we've got an aging population, you're all going to live longer, and the cancer burden is going to go up. So I think about this as kind of 3 hits, really. So you've got a neonatal microbiome, probably you get antibiotics in early life, and that affects microbiome assembly before the age of around 3 years of age. So that means your microbiome is not in the right place to engineer the secondary metabolites that you need for gut health. Then through a kind of 20, 30, 40 years of lifetime, you perpetuate that state through a poor diet or exposome interactions that lead to chronic inflammation and ultimately adenoma formation and ultimately cancer. The critical importance of the gut microbiome is that actually this is going to be important for drug metabolism. So these bugs are not only important for metabolizing food, they're critically important for affecting the efficacy and toxicity of the drugs that you use to treat cancer through a large scale of mechanisms that we've coined the timer mechanism. All right? And so if you take a drug like irinotecan, it's reactivated in the gut by beta-glucuronidases found in E. coli, and it's that causes toxicity. There's been a lot of interest in checkpoint inhibitors in immune modulation of cancers, particularly melanomas, because these drugs, which we just assumed had no effect on the gut microbiome or vice versa, it turns out are closely linked. And this study came out. I highly recommend it to you if you've got the stomach for reading a bioinformatics paper. But I want to just make one point, right? This is just beta theta iota micron, right? And this is lots of different drug targets. These are enzymes that you find produced by the bug, and these are secondary metabolites. So within beta theta iota micron alone, their genes can metabolize 18 different drugs to 41 distinct metabolites. That's just in one species of bacteria. And I started by showing you global variation in individual species. So if you want your drugs to work in a cancer patient, you have to have a very good understanding of specific targets or specific strains within those patients. And just one example of how we can translate that into practice. Indoles, so a dietary substrate tryptophan is converted to indoles by tryptophanase, which is a bacterial lyase, which you can see there, which is then further conjugated in the liver to form indoxyl 3-sulfate. Why am I telling you about this? Well, I'm going to tell you that it's important because actually it's a little bit more complicated than that. There are 3 different pathways. This is work by Leslie Hoyes and the group at Imperial. But actually, quite a lot of different bugs are important in the prokaryotic metabolism of these pathways. I started by showing you graft versus host disease in hematological cancers. So this is Ernst Holler's work, and I must thank him for sharing this with me. But effectively, you can predict your likelihood of having a graft versus host disease bad reaction or survival after treatment with bone marrow transplantation in these hematological cancers based on your ability to secrete an indole. And that correlates specifically with the type of bugs that you have within your gut. Why is that important? Well, it's important because you can intervene. So in an animal model, you can give a derivative of the indoxyl. So in this case, they gave, I think it was indoxyl carboxylic acid. And these are to animals. This is an animal model. So by giving a dietary substrate to a mouse model having a bone marrow transplant, you improve survival by modifying the gut microbial structure and function. So if I showed you this graph at the beginning, I think this is a bit more complicated. I think actually engineering the microbiome for improving cancer outcomes has to happen much earlier in the treatment cycle. It has to happen before you started. It's about improving robustness. And when it occurs, it's about engineering the microbiome in a much more specific and personalized way and looking at specific molecular targets, for example, indoles, to improve outcomes. So we need to reimagine what an oncological trial looks like. Because if you're looking at just one moment in time, you're missing perhaps critical changes to the gut microbiome that might define how you're going to treat that patient later on, maybe when they've recurred. And we need to redesign studies and sample these patients in a different way. No cancer trials currently do this. None. Zip. We have no idea really in clinical practice how the gut microbiome influences patient outcomes. And you're going to hear some other work about FMT, so I'm not going to talk about that in a second. The good news, though, is that there are lots and lots of different modalities now at our disposal. We have a completely new toolbox to try and prevent and treat cancer that we never had before. So the future is very exciting. And this was a talk I was at in the US quite recently. Just because I'm a surgeon, I've got to have at least one surgical slide. And this was preoperative changes in animal models for reducing the blossoming of collagenolytic enterococcus. So these bugs are really bad because they chew down all the joints that we make in the bowel and cause the bowel to leak, right? So if you change the diet of these mice before you do the model to change community composition, you can improve operative outcomes, which to me is quite important. So the greatest revelation for me as a surgeon has been the critical importance of diet for the prevention of the disease. It sounds completely obvious. I know you know all this. The majority of you are dietitians and nutritionists, right? But I'm a simple surgeon, so I was late. But also how we can modify the gut microbiome to improve oncological outcomes by targeting the gut microbiome. I think the African microbiome is critical to understanding some of these pathways. It's a precious resource that's really quickly disappearing. Lots of people did this work. Thank you very much.